Hi, today we're going to be doing problem 18.46, and this one is asking us to find the Ka of a weak acid. So first thing we're going to do is write down what we're given. So we have a weak acid labeled as Ha, and it has a pH of 4.88. And what we need to find is the Ka. So we're going to think about what we know about Ka. Ka basically equals the Kc, the equilibrium constant, times the concentration of H2O. We learned that from our chapter 18 stuff. So to find Kc, we can write out a chemical equation problem. So we have our acid plus H2O. The reason why we're adding it to H2O is because Ka is basically the amount that the acid will protonate water. So when you see Ka, you gotta add it to water to find Ka. So the weak acid plus H2O, and then the acid's gonna protonate water, so you're left with A minus plus H3O. So now to find Kc, we're gonna have to do an ICE. This stands for the initial value, change, and then equilibrium. So the initial value that we have, that we're given, we had 0.035 molarity of our acid. So we're going to put that as the initial value, 0.035. And then water we're going to leave blank because that's a liquid. And then your ion over here is going to be 0 to start with, and your H3O is going to be 0 as well. Now the change is going to be subtracting X from your acid, because you're going to use some of your acid to go to your products. And then water we're going to leave blank again, and then it's going to be plus X for your products. Because for every mole of your acid you use, you're going to produce a mole of each of your products. And so your equilibrium concentration is going to be 0.035 minus the change, or plus the change, which is negative X, so it's 0.035 minus X, and then your ion over here is going to be X, and H3O is going to be X. Now we can find your equilibrium constant, which is going to be the concentration of your products, A minus, times H3O, plus, over your reactants, which was your acid and water. Now we know Ka is equal to Kc, equilibrium constant, times concentration of water. So if we want to find Ka from Kc, we just multiply this by H2O, which would cross out the water. Water would cancel out. So we have A minus times H3O plus all over your reactants, which was the acid and water, and then times H2O, because we had Kc right here, and then times H2O. H2O is going to cancel, so you're left with Ka over here, which will equal A minus times H3O plus over your weak acid. Now we can plug in our equilibrium concentrations. Notice how we have to use the equilibrium concentrations here. We cannot use the initial or the change. So we're going to plug in X for concentration of A minus and X for the concentration of H3O plus. And then your acid, it changed, so we have 0.035 minus X. So now we have an equation to find Ka. Now, how are we going to find X here? Well, in the beginning, they told us that the pH of our solution is 4.88. So we can convert pH into something else we need. Our equation that we know for pH is negative log of the concentration of H3O plus. So see here we have our hydronium ion right here. So we can use pH to find our hydronium ion. The way we do that is convert the equation to H3O plus equals 10 to the negative pH, which is going to be 10 to the negative 4.88. So our concentration of the hydronium ion is going to be 1.318 times 10 to the negative 5 mole. So this equation right here, how we convert from pH to hydronium ion, you need to know how to do this. Go back and forth between the log. So we'll plug this in here. This is equal to x. So we'll plug this in for x up here. So we have 1.318 times 10 to the negative 5 times 1.318 times 10 to the negative 5. There's our two x's at the top. And then we have 0.035 minus x, which is 1.318 times 10 to the negative 5. So we have everything plugged in here. Now we can plug this in our calculator and get an answer for Ka, which will be 4.965 times 10 to the negative 5. And this goes, we can round this out to 5.0 times 10 to the negative 5. And this, think about whether this looks right, 5.0 times 10 to the negative 5, that's very small, which makes sense because we have a weak acid. So if it was greater than 1, then we'd have a strong acid. So our answer makes sense, and we solved our problem.